So everyone, I do have a link up here with all the slides. That way you can follow along if you want to, or because there is code, if you want to just grab a picture of that, you can check out the code later and not have to worry about trying to follow along as we're talking. I will have this at the end of the thing too, so if you decide, hey, this was actually an okay presentation, I want to get it later, also good. That way you're not worrying about it afterwards too. All right, so hey y'all, my name is Paul Ruiz and I am a developer relations engineer with Google. So while my team actually covers a variety of ML topics, my main focus is on mobile and IoT devices. So this year at I/O, we announced an updated set of products for on-device machine learning called MediaPipe Solutions, which is currently in alpha. We're working on getting all that together though. I think hopefully the end of the year we should be at a good spot. Overall, I think my goal here today is just to make sure that you can walk away with a vocabulary around machine learning, know how to apply those concepts with MediaPipe, and then have an idea of where we are going with this with mobile in the future. That way you can actually add even more ML features to your apps. So before we start, I did want to go over and cover a few really high-level machine learning concepts. So while a traditional program is going to take a known input and a known function, or essentially a set of rules, to produce an output, machine learning actually takes a set of inputs and a set of known outputs, and then it tries to figure out what the function is between the two so that outputs can be generated based on new inputs. This process is actually called training, and it's one of the main technical things people think of when they're working with machine learning. Though, honestly, it's a little bit outside of the scope for this talk, just because as Android developers, we tend to be given a model that somebody else has already worked at optimizing and solving a problem with. That said, I am going to go over where you can learn a bit about training a new model using something called transfer learning just a little bit later. So the next thing to know is that machine learning models do not provide exact answers, nor do they really always give you the correct answer. So what models do is they make predictions based on what they've learned during the training phase. So the biggest suggestion that I have here is that you really shouldn't rely 100% on what the model says, but it should be used as a tool to help guide decisions. And then finally, machine learning allows you to do things in your apps that are just really difficult with more traditional programming techniques. So even just a few years ago, it would have been incredibly difficult to recognize a bird or a diseased plant in an image or video. But now we can actually do that with just a few lines of code. So today I actually want to go over how you would do that amongst other things with MediaPipe and Android. So MediaPipe is for on-device machine learning. This means that it is meant for running machine learning inference directly on a device rather than training. So instead of having to send your data off to a server somewhere for processing. So this is going to give us 4 major advantages just from that one single attribute. We can run inference more quickly since we're cutting out the transit time. We can use machine learning on a device when the internet is down or it's unavailable. So say somebody is on a subway or on a rural area. Privacy is preserved since the data is never actually leaving the user's device. And then offloading ML inference to the end user is actually going to save a ton of money compared to doing everything all on the back end. So to give you an example of this actually, if you use Google Meet, you know how you can blur the background on the image so it's just you and then blurred? That's actually happening on the end device rather than sending your video up to a server somewhere, processing it there, which costs a whole bunch of money, and then sending it out to everyone else. So offloading that, especially when you start scaling this to millions plus users, is just going to save a whole bunch of money on those back-end costs. So with that, models are actually at the heart of on-device ML. So generally you would take a single model, like one for object detection, and then bundle it in with your program. So this will let you customize single operations for your purposes. They're kind of fairly lightweight, and they can be optimized for different device constraints, including memory, computation, power storage, or any of that kind of thing. It's actually super useful too, considering the majority of Android is about trade-offs and trying to figure out what is going to be the best solution for your situation. So then there's ML pipelines. So these are going to streamline the process from your initial raw inputs all the way to your output results. So this usually involves some domain-specific preprocessing, such as resizing and rotating images, end-to-end pipeline acceleration for improving performance on your models, and then a way to deploy these models across multiple platforms, which itself is actually pretty complicated once you start working with Android, iOS, web, any of those other platforms. So the problem here is that regardless of whether you're using a model by itself or an ML pipeline, you're still going to require some general machine learning and domain knowledge, as well as put in a bit of effort to design, build, and optimize your features. So this does get complex, and it's one of the biggest challenges that we see from developers when they want to add ML to their apps, which in turn is going to limit a lot of the cool things that developers could do to make even better web, mobile, and IoT applications. So that's actually why we're working on this MediaPipe edition. So the goal here is to abstract a lot of that complexity away with a new tool called MediaPipe Task, which is going to handle flow control, some pre and post processing, and synchronization, amongst a whole lot of other things, while also doing inference. So we want to make this as simple as providing the input and then receiving the results, all without requiring a whole bunch of boilerplate for our developers. So in addition to MediaPipe Task, we actually have something else called MediaPipe Model Maker. So the whole idea here is that you can take your own set of data and then create a new model, or a model task bundle, but just something I'm going to talk about a little bit later, where it's multiple models that are put together into a stream to use. But it is stuff that can be based on existing templates, particularly for the MediaPipe tasks that are supported. This is also going to allow you to customize things to increase performance and other stuff that can go with it. If any of you are familiar with like TensorFlow Lite Model Maker, it's the same exact idea. It's just made so that it is optimized for the solutions that are available with MediaPipe. And then finally, we actually have a tool called MediaPipe Studio. This is basically just a web tool that will let you test specific tasks without having to go through and create a brand new app. Though there's actually plans to add a new feature to it as well, where you can upload your own data and have that create new models for you. Basically following a general template if you don't need to customize or do anything else special with it. So before I really dig into how to do this all with Android, I did want to point out that one of the important features is that MediaPipe Task is available across a variety of platforms. So the underlying work is actually happening in C++, and then we're building APIs on top of that for Android, web, Python, and iOS. That said, iOS, the CocoaPods and all that for that just came out last week. So I am in the middle of getting samples together, documentation, all that kind of fun stuff. So it hasn't hit parity yet, but that will be soon. And then along with that, I actually just got the green light to work on Flutter like last week. So the GitHub is already launched. We are working on getting that done. I'm working with the Flutter team. So that should be soon if that is something that interests you here within the upcoming months. So with the combination of individual models and combined task files, we're actually aiming to support like 20 different ML features by the end of the year. And we're currently at about 15. So the current focus is primarily on natural language processing and vision, though we also have some audio ML support, and then we have this section that's just called more. That's going to be things like speech, recommendations, and some other stuff I'm going to talk about later in the presentation. So I do want to start by going over image classification, since it's kind of the hello world of machine learning. So essentially, this looks at an image, and then it assigns one or multiple labels to that image, depending on the model that you're using, to try and classify what's in it. So for example, with a single label classification model, this image of a cat will likely appear as cat, since it's the most pronounced item in the image. And then if you're using a model for multiple labels, then you might see cat, rug, or toy as possible labels just all together. Cool, so I actually want to take a quick look at how this classification happens. So the underlying model that I'm going to cover is using something called a convolutional neural network. So this tool's main way to approach image classification is to look for patterns within that image during training, and then look for those same patterns in a new image. So if we look at the cat image, we can actually see that it's looking for ears, eyes, and nose, and those are the patterns that it's detecting here. Whereas if we go to a new image, we should be able to find those patterns, or at least most of them, in order to say with some level of confidence that this is also a cat, just because it is recognizing those same patterns. So the next thing to know is that this classification happens across multiple layers of an image. So for example, Android may provide an ARGB image. Alpha layer doesn't actually matter. It doesn't give us a ton of information. But then when you look at the rest of the colors, they're able to kind of highlight different patterns that might be in the image itself, so that they are noticeable across other examples when they come to them. And then finally, images may need to go through a few pre-processing steps to scale, shape, or rotate them so that they match the image parameters for that model and what it was trained for. So for example, a model may have actually shrunk the training images down to 32 pixels by 32 pixels, or that might actually be what was given to it. So your Android app is actually going to need to do the same in order to perform classification. So this is that pre-processing step that I had mentioned earlier. So here you can actually see a quick example of image classification working in Android through a live camera feed. So I want to go ahead and just go over the code for how you would make something like this work. So the very first thing you want to do, just like with most libraries for Android, is make sure you import the dependency. So in this case, I'm using one for vision. We also have one for audio and one for natural language processing. I will go over that as we get to those topics, though. So the next thing to do is to create the actual object that is going to do the classification for you. This pattern is pretty similar across all of the tasks that we have with MediaPipe, so I am going to take a second to just kind of go through it. So there's two levels of options that will be combined to create the classifier. The first is the base options, which we can create using a builder pattern. And then one of the properties that we can associate with that base options object is the delegate. Delegates are kind of cool. It's the thing that you use for hardware acceleration, which is a part of kind of that pipeline that I was talking about earlier. So in our case, we actually support the CPU, which is slower, but it is on every device, and then the GPU, which is going to be faster, but it might not be supported by a given model or a device that you're working with. And then for these next two lines, we're just going to set the path to our TF Lite model and then create the base options object. Now, because this is for on-device machine learning, that model does already need to exist within your app at the time of inference. So you can do this either at build time, so say you have a download.gradle file that will pull down the model from a URL, or when you actually start up the app, you can pull it from a remote source, save it in assets, and then use that to initialize your classifier. Also, one thing I'm going to point out here too, I'm actually using a TF Lite file here rather than a task file for image classification, specifically because image classification is a singular task that doesn't need to run multiple models in series. But I'll talk a little bit more about task files as we get to it. So this next block is where you're going to create the image classifier options that are going to be specific to image classification rather than just general task. So here you're actually able to set the minimum score threshold, which is how confident the model needs to be in a classification before it even returns those results to you. So if you're okay with 30% or better, then you can set it for that. If you have a very particular thing that you need from classification, you need to say, hey, 95%, you can actually set it for that, and it won't return anything that falls under that threshold. We also have the max number of results, so you can say, hey, I only need one of them, or I need 5 of them, or however you want to do this, and it will return n number of the most confident items. And then we have this running mode. So running mode is going to be how you tell the classifier if it needs to work for a live stream, a still image, or a video file. Each of those running modes are going to have their own unique properties that you have to be aware of and take account for, so I will talk about that a little bit as we move forward. And then for this last step, to create the initial options, you just want to associate the base options that's available for all tasks in that first block on this slide with the new image classifier options that you're creating. So on the last slide, I did mention that you have different running modes for live stream videos and images. So if you're using a live stream for classification, then everything is going to happen asynchronously. So because of that, you actually need to associate the results and error listeners with your builder and able to get those results back. So if you don't have it, I actually think it will hard crash on you if you're trying to use live streams, just because it doesn't have anywhere to send those results back to. And then finally, you can just create the new options and then use those to create the new image classifier object that's going to handle pretty much all of the major work. I'm not going to get too much into detail here, but basically our vision samples are using camera X just to retrieve camera frames and then create an image analyzer to process those frames. So the thing that actually matters here is that we are using ARGB or RGBA, whatever we order it is, 8888 formatted images. That way we have those 3 layers that matter as well as the transparent one that we can just ignore. And I'm also using a 4:3 ratio here because the default model that I'm using for the example was trained for 320 pixel by 320 pixel square images. So this is kind of the closest option that we have so that we can format into that size without losing a whole bunch of information. So once each frame has been preprocessed, we can send the image proxy object to be converted over to a bitmap buffer and then classified. Basically it's just going to take what comes from the analyzer and then work with it to format it into the way you need based off of that image proxy. And then from there, you just want to make sure that the image is rotated to be aligned with what our model is expecting. and then create a new MediaPipe image that's going to be classified using the classify async method. So I'm actually using classify async here because it is a live stream. I think the next slide or the slide after, I talk about how, or I show how you could do this for still image, which is just going to use the classify method. Actually, yeah, that's exactly there where I am. Cool. Cameras are difficult. I hate them. So if you wanted to just use a still image, this is basically how you would do that. You basically take the same exact still image, you turn it into a MediaPipe image object, and then you just call classify to classify it synchronously to get those results and return them wherever within your app. Cool. So the next thing I did want to talk about is object detection. The code implementation is actually going to be very similar, so I'm going to just go ahead and skip that. You've already seen the code. I will have a link to the slides at the end again too, so you don't need to worry about any of that. So not only does object detection help you classify items, but it does help you find out where those items are based on the input. So actually what's interesting about object detection is it's made up of 3 separate functions that will give you the end result. So the first one is what you would traditionally call detection, where the model is going to try to determine if an object that it was trained for even exists within the frame. Generally, this is going to use something called statistical analysis. There's a whole bunch of detail that will go into that that isn't really relevant for this part, but it's something to know if you do want to look into it. So after that model has predicted that the object even exists, it's going to attempt to recognize or classify that object, just like we saw with image classification. And then the final step is called localization. So this is the process where the model is going to determine where the object is in that image or camera frame. So the real tricky part here, data is never uniform, especially when you're actually using this like in a practical example. So there are a couple different situations that you should at least be aware of. So if you're talking to somebody who's done the training, you can find issues, fix them, and kind of move on with your life. So some of those would be like overlapping objects. So let's say you have 2 objects that the model was trained for. One of them is in front of the other, so you kind of only partially see one. You're going to get a false negative because of that. You might also have objects that are different scales, or they might be rotated. So if your model was trained only expecting one orientation for an object, it may not detect it once it's been rotated. And then the last one is just very similar to overlapping objects, but maybe you have one object that's just kind of partially off frame. There's some techniques to deal with that. Just understanding that that is something that can go wrong is super useful when you are either training it yourself or talking with someone else. And then the next thing I want to talk about is landmarking. So using these APIs, you can actually find specific points on a person's hand, face, or just general poses. So here you're going to see that I'm using gesture recognition to classify a thumbs up, thumbs down, closed fist, or open palm using a pre-trained model that we provide. So similar to object detection, gesture recognition works through 4 separate steps. Actually, each of these steps, though, is made up of its own individual model rather than steps that are within a single model. So each of these models actually has a variety of steps underneath it that you have to take into account. You don't actually have to take into account, that's the whole point of this. So the first model is going to attempt to detect the presence and location of a hand before it even moves on to the next phase. And then that phase is going to attempt to locate useful landmarks on the hand, such as your knuckles, fingertips, or the central base of the palm. The third model is going to convert those landmarks into a vector embedding. I'll talk a little bit about embeddings later too. They're actually a very big topic in machine learning. So understanding those, even at a high level, is super useful. But once you have those vector embeddings, they are just fed into the final model that is going to attempt to recognize the gesture based on those landmark information. Everything is very similar to the other vision task, so I'm going to trim it down to just these options that are available that are very specific to landmarking. So this is going to be how confident the model is that the hand even exists or moved in the frame. So the whole point of tracking is that it basically checks to make sure that the hand is still there or that it kind of understands where it's moved before it even moves on to the next models to run. So this is going to significantly speed up recognition if the hand is still in frame or if it has moved out and you don't need to actually hit up those next models in the process. So I have talked a bit about MediaPipe task. I am going to get back to that in a second. It is the more relevant part to Android developers, but I did want to bring up that we do have this resource for retraining models with new data. So this is the MediaPipe model maker that I had mentioned earlier. So let's say you wanted to train a model for American Sign Language. So this is actually an example I get from a lot of students, because they want to use this for school projects or any of that kind of thing. So in this case, I'm holding up the letter I, but our default model doesn't actually recognize that as anything. So to retrain a model that does, you can use Model Maker with your own data. So to give you a better idea, actually, I already put together this collab where you can go through step by step. We provide the data for rock, paper, scissors, and it will train a new hand gesture recognition task file for you that you can then use with MediaPipe Studio or your own Android apps or the samples that we have up on GitHub. So what actually is going to happen with this is you can see I do the thumbs up, thumbs down in a second, and it will recognize it as like a none category because it just doesn't actually recognize it because it hasn't been trained for it. But if I do rock, paper, scissors, it does detect those because that is the data that the model was trained for. Before I move on to, I did want to point out that there is more functionality that's going to be coming out with this here pretty soon. We are working on multi-handed gestures right now, so you can do like a timeout or like a little two-handed heart thing. So it's not just one-handed gestures that you can do. So moving on to pose detection, hands have 21 points that you can see, whereas the stock task for this has 33 landmarks that are actually tracked in three-dimensional space as the user moves around. So out of curiosity, have any of you played with MLKit's pose detection API? Nobody? Really? All right, well, cool. Well, ours is better anyway. Same idea. This is the stuff that is actually built on top of. So we are giving you more like access to customize and improve and do better things with it. So, and then there's face landmarking. So as you might guess, this task is going to help you just find landmarks on a face. So the default model for this actually detects 478 3D landmarks in real time. And it's actually only using a single camera, which is really cool. So it's tracking all those points as the person moves or faces a different direction. And then similar to hand gestures and poses, this pipeline also has multiple models. So there's the detector that's going to operate on a full image, one that's going to figure out where those face landmarks are, one that's going to basically look at those locations and then predict like a rough 3D surface, and then one that's actually going to find attributes of a face, such as eyebrows raised, smiling, eyes closed, and like 50 other things that you can add in there. So along with that, we actually have a face mesh rendering mode and a transformer in the current solution. So this is going to help you with wrapping textures on the user's face for different augmented reality features, things for like testing makeup, glasses, filters, special effects, and really anything else that you can come up with. And then this is actually really cool too. So since the earlier gesture recognizer really only worked with static gestures, we are working on a holistics API that will combine multiple landmarks together in just one call. Over a period of time, you can record that, and then you can pass it to another TensorFlow light model that we have up from a Kaggle competition that will basically take those landmarks over time to do sign language classification that's actually dynamic rather than just still images. So here you can see that I'm able to do shower, donkey, and frog, but it's actually able to pick up very similar gestures for things like cow, which is, instead of this, it's just this, and pig. And then I think it's also trained for 200 different things, just with that model that's stock and already online. So moving on to the next thing, we do have support for image segmentation, so I wanted to kind of dive into that because it's also kind of cool. So this is very much what you were already seeing with Google Hangouts and getting the blurred backends and all that stuff. So here you can see that we have a person, and we can modify all of the pixels either around them or on that person to basically highlight things or figure out where they are. So what's actually interesting about this task is it's looking at every pixel in relation to the pixels around it to attempt to classify an individual object with kind of some level of confidence, but again, this is machine learning, so everything is some level of confidence, and yeah. So this is actually using something called a category mask, where every pixel is assigned to that given category based on what it's most confident about. There's also different options too, where you can say, hey, my model is trained with 23 different categories. Give me the confidence for all of them, and I can do whatever I'm going to do with it. And then the other type of masking is called a confidence mask. So instead of focusing on what the category is, it's going to try to focus on how confident the segmentation model is in the label that it's assigning to that pixel. So for example, I'm actually setting this one up so that any pixel that is over 50% confident is going to come back as a transparent pixel. And then the rest of them are just going to be blurred based on the level of confidence for that label. As long as they're over some threshold, which is why it's kind of noisy. I think I said anything over 50 is going to be transparent, and then when you get to things that are like 1%, they're also pretty close to transparent. That's why a lot of this is just kind of low percentage noise. And then she does a little flip. It's awesome. Anyway. So another technique that developers might find useful is something called interactive segmentation. So honestly, this is going to work in a very similar way to the other segmentation features that you just saw. But now it's going to focus on grouping items together to return essentially one whole piece rather than giving it a specific category. So here you can actually see that I'm able to tap on the various stuffies, and they're going to segment out to each specific one based on the area that I'm clicking on. We also have support for doing kind of like a squiggly line, so if you wanted to select multiple within an area, you can just give it that area. I will have a sample up for that soon. It works. I need to do the PR hopefully next week. How are we doing on time? We're actually doing pretty good. Sweet. So the next thing I do want to talk about is audio. I'm going to keep things simple. I'm going to just do audio classification because it is the most common use case that we are going to see from developers, that we do see from developers. So there's a few different ways to represent audio data in a visual way. So the first is the waveform, which you can actually see here. So this is going to represent sound pressure. You can kind of think of it as just volume. There's some other technical aspects to that, but it's over a period of time. And this doesn't really give us a full picture though, because one sound may look very similar to another, like a car horn and a siren. So the next option to discuss is the MEL spectrogram. So not only does this measure time against sound pressure, but it's also going to track frequencies, allowing you to pick out individual sounds with a bit more ease. So when you're looking at a spectrogram, really all you have to remember is that X is going to be time, Y is going to be that pitch or the frequency, and then the color is the volume. So to give you an idea, actually this spectrogram and the waveform on the last slide are both me saying the word hello. But with the spectrogram, you can actually see how the O is a bit more pronounced and drawn out at the bottom there, where it's kind of that yellow that drags on. So with that in mind, I did want to take a quick look at an example of a harp playing descending notes. So this is actually happening with the spectrogram as well, but here you can see how the frequency is going to shift those spikes lower with each note, while the volume color is also going to increase. And then in this video, I actually set up a live stream where I am repeatedly saying the word right. Since this word does have a break in the middle of it, you can see the initial right followed by that higher frequency T after the break. So with that all out of the way, a lot of the techniques for image classification are also going to carry over to audio classification once we start considering everything in terms of a spectrogram. So as we saw with the word right, it does look similar when said multiple times. But this is also mostly the case with different people saying the same word. This actually gets a lot more complicated too once you start bringing in dialects and accents. So like even when I'm speaking, I'm saying right here with that T pronounced, but I am originally from Central California and I have my own kind of accent that goes with that. So like I say right instead of right. We also say other things like apricot or pecan and some other things that you don't really hear in other parts of the country. There's also like accents that drop R's, like in Boston, you'll hear people that drop their R's at the end of words. So with that, you do have a whole lot of other things to take into consideration when you're doing audio classification, if you ever do get to that model area of it. This whole field is called computational linguistics. I can actually go pretty far into it, and I love it. So talk to me afterwards, and I will do that. Anyway, so with audio, you can actually take a chunk of a recording, like 1 second as an example, and then run classification on that to try to identify sounds. However, you can actually see in the first instance of speaking that the word is split right down the middle. So likely this won't be classified correctly when it's compared to the second instance that's going to fall completely within that quarter segment. So the way you can address this is through something called overlap. So basically the input audio is going to be stored in a buffer that continuously gets filled with the latest audio while also getting rid of the old data at a consistent rate. So if we have a set of 1 second clips that we're analyzing in order to match our model, but we add a second set of inference that just kind of has a shift of about half of a second, then we end up running 2 different streams of inference to try to catch the things that wouldn't be caught by the first one. So here you can actually see how the first instance of the word right, while it was in the middle of that first segment with the blue line going through it, it falls perfectly within the first pair of orange lines, which is a part of that overlap. So doing pretty good, cool. So to use audio classification in your apps, you will just want to start by importing that dependency, just like you would with anything else in Android. So this one is the MediaPipe task audio that you're going to be able to bring in. Let's see, so I am going to skip some of the code that's in here. I already took out the slides, basically because it is very similar to what we already saw with the other task. There is common code, so it's not worth boring you with it even more. So where this starts to vary is that you do need to create a audio recorder, which, as you might guess, is responsible for recording device audio. So this is going to need the sampling rate passed to it, the channel configuration, and then the buffer size for storing in audio data. There's actually some implementation details that are hidden here too, which is kind of cool, such as the audio recorder using the PCM format, or pulse code modulation, which itself is a subset of wave. Another detail you don't super need to know about, but when you do start working with audio, Android and audio is never really consistent. It's kind of similar to using Bluetooth or using cameras. Somebody broke something, and understanding where is always nice. And then as for buffer size, for storing that audio data, I'm just using the sampling rate times the expected input length, which is 0.975 for the model that I'm using. And then I'm multiplying that by the size of a byte, and then I'm just doubling it to make sure that there is enough data there for overlapping and processing before it moves on to the next chunk of data. And then the next step's a little bland. It's just a runnable. It's going to pass information to be classified over a little bit later. And then everything else in your code is to start recording, then figure out how often classification should run from an executor along with the amount of overlap. So here you can actually see that I'm using that static 0.5 on the fifth line there. That is showing that I am using essentially half a second of overlap, which is going to be like the orange bars that we saw in that first spectrogram. And then from that runnable a couple slides ago, you can just extract the audio data that was passed in a recording, then call MediaPipe's classify async method to do the real classification that is going to be returned to your result listeners. So if everything goes well, which hopefully, you should be able to consistently record audio on a device and then classify it based on the model that you're using. So in this case, I'm actually using one called YamNet, which has like 500 different categories that it can recognize. Like the music that you're seeing in this example, where I just kind of put on something on YouTube, held it up, and tried to get as many things as I could out of it. Cool, so the next thing to go over is natural language processing. It's essentially just text. It's nothing super fancy, but it is something that is super common and useful. So in this example, you can see text classification happening where some text is entered, and then it's classified by how likely it is to either be positive or negative. I'm not going to get into a ton of detail about how natural language processing works. We do have a full video series on the TensorFlow YouTube channel. It's going to cover this in way more detail than I ever could. I think it's like 2 hours or something. But for what we're working with, the most important part is that letters or words are matched up to a numerical value through a process called tokenization. And then those tokens are then assigned a weight towards a classification, such as positive or negative, to match the earlier example. So to do this yourself in Android, you first need to import the MediaPipe text task dependency. And then from there, you kind of do the same sort of options building that we've seen in the other examples. Plus, you're going to create the actual text classifier object. And then finally, since you don't need to record any live data, like you would with audio or camera streams, you can just call the classify method on that classifier, and that's going to give you the list of results that would be associated with that bit of text. I do want to talk about text similarity too, just for a second. This is actually pretty quick, but it's kind of interesting. This is where embedding is going to come in and how you would do similarity testing and all that fun stuff. It's also just more interesting than another classification example, because you've already seen 3 and it's just kind of boring at that point. So this is using something called cosine similarities. So basically you can take 2 sentences that you want to compare and then turn each token into its own axis within this graph. It doesn't even need to be a 2-dimensional graph. There's actually some other cool stuff that goes along with that, but it's outside of scope for this. With that, you can then start counting each of the tokens per block of text that we're going to submit to create a vector based on words and their frequencies. This is going to give you the slope and the magnitude, which is the definition of a vector, so that kind of makes that cool. So here you'll see I have hey world and hello world, and each of these are broken into their own independent vectors, and they are added together to give us this orange one and the blue one. So once we have the two vector representing the sentences, then we can measure the angle between them, then take the cosine of that to figure out how similar they are to one another. So here we can see that we have 40 degrees in between hey world and hello world. If we take the cosine of that, we get 0.77. So the way cosine works, you have -1 to 1. If it's -1, then the sentences are absolutely nothing alike, whereas if you have 1, then they are completely alike. It's the same exact sentence. So this kind of falls in between those. So just like the other examples, start by creating all of your option items, and then create the text embedder object. After all that's done, you can actually take the string of the two sentences that you want to compare, and then turn them into embed objects. One thing that's also cool about this, there is image embedding and audio embedding that are also available right now that you can use the same exact idea with. And then finally, you would just call the cosine similarity function to get the return similarity value. So super easy, very little bits of code, but then you can compare those and then use that as a building block into additional features as you start building them out. So that is it from the coding side. We're able to hide a lot of that complexity just because we are using MediaPipe Task for this. That way you can focus on creating your features without having to get too much into the details that are happening under the hood. I know this whole talk has been about the details that are happening underneath, but it does get easier when you're actually just implementing this. So here you can actually see those same two sentences that I mentioned earlier, so hey world and hello world. Both of these are being added to the text field. I am getting the 0.77 for the cosine value, so it is a 40-degree value in between those two like full-on vectors. So to wrap it up, I did want to touch on generative ML, mainly because it is one of the more interesting things that's out there. It's also one of the things that's more fun for us to work on, so it's exciting to see it actually coming through. A lot of this is out soon. It does work. We are just optimizing it at this point. So the first topic is style transfer, and in terms of tasks that we provide, specifically face stylization. So for this one, you're going to train a model that uses a single reference image. So you don't need hundreds of images, you just need one, and it will kind of figure out what the style is for that. So you can see how we are able to apply that reference style to a new face to create the stylized image. So here you can see I actually have a 1910s Gibson image, and that's being applied to a current picture to get that stylized version of, it's actually my wife, but this person. Yeah, and then actually if you're interested in this too, there are research papers out there for something called JoJoGAN, Jojogan. So the way this is going to work is using something called a generative adversarial network. I'm not going to get too far into the details. There's a lot that goes with this. It is super interesting though, so I will talk about it later if you want to. Essentially though, you have a generator that is going to create an image, and then you have a discriminator that's going to try to determine if that image even matches the type of final image that it expects. So this is going to end up going back and forth, basically improving against each other until the generator is able to create a new image that's able to fool the discriminator. As soon as it's able to trick the second part, we just say, hey, it's good enough, send it out there. I don't know if any of you have seen the movie War Games when it's playing tic-tac-toe against itself, but it's very similar to that idea. Cool. So another cool thing about this too is that you can even provide an alpha value to that generation to only apply the reference style to a set degree. So let's say you have the original image here that's using 0% for the stylization. I'm just progressively adding 25% more to that style until I get one that is 100% done. But if I had a style where it would be fine to only have it partially done, then I would be able to set this alpha value, and you can see how that would progress over time. And then the second type of generative ML is actually image generation. Again, this is actually all happening on device. It doesn't go out to the internet at all. It is completely running a model on your Android phone, which is kind of cool. So rather than the GAN technique, which a lot of other generative models are using, we're using something called diffusion. So essentially this works by taking some text, figuring out what the keywords are related to that model, and then creating a large enough, or like a large amount of initial noise, which is that staticky part that you're seeing there. And then essentially it's going to run through multiple iterations to try and denoise it to make sense out of that static and get it into a better spot. Actually, what's cool about this too is we're using a technique called model distillation to actually reduce the size. So even though the model is still in that like early prototyping phase and it is kind of large, we're doing really cool things to bring it down to a reasonable level so that we can release it for people, and then you can essentially do model maker stuff as well to customize it for very particular task. So let's say you had a keyboard app and you wanted to generate GIF stickers or emojis or whatever, you'd be able to use the same exact idea to make custom emojis that you send to your friends or whatever. You can actually see too that it's doing this one over 20 iterations. It takes like 20 seconds to run. It's only that slow right now in this example because I'm showing each intermediate step. So if you ditch the intermediate steps, I think it comes down to like 10 seconds, and then a little bit less if you bring it down to 20 iterations. So kind of wrapping up here, while there's quite a few other on-device tasks that are being worked on, including text generation, same idea that you have with like large language models and that kind of thing, we do currently have a whole lot of things that we are adding right now. These are our current existing samples. I have all of the Android ones, web ones, and Python ones up there. I'm adding the iOS ones right now. There's more coming. I just need to get time. But we are making progress. There's already the 15 that are up there right now that you can test out. And then since we are working on building a whole bunch of this stuff out right now, there's a lot of changes happening, and it's all happening like at once. So if you want to keep up with that, you can join the MediaPipe Solutions Google group to get basically the announcements as they come out. I am starting to write those and send them. You can reach out to us at this email, and then you can just check out the main documentation pages over at developers.google.com/MediaPipe. On top of that, please find me. Feedback is great. I want to know what you're doing with machine learning, why you're not using it, if you are using it, what you like about it. Tell me what you hate about it, because then we can avoid that. This is still an early product, so the more we know about what to avoid, the better it is before this hits like an official release and it's just kind of stuck. I will also bribe you with stickers. I had stickers made for this, so come see me. And then here is the slide deck there too, so if you want to get a picture of that, you can get all the code, all the links, all that kind of fun stuff. So yeah, thank you.